In this video, I'm going to do a row reduction on example matrix, and I'm going to talk about what it is, the objective of row reduction. So we have to define some terms, some names, and specify what we're looking to do. So we're interested in this thing called row echelon form, and it's a property of a matrix that if a matrix is in row echelon form, it's going to have 4 different properties that it satisfies. The first thing it needs to do is have all the leading entries be 1s. A leading entry is the first non-zero number in a row. So basically you look from left to right, and the first thing that's not a 0 has to be a 1 in every row. The second requirement is that all entries below one of the leading entries is equal to 0. And that means going down the column, whenever you have a leading 1, everything below it is 0. So that's the leading entries are colored in green, and the entries below them are colored in blue. Alright, the next thing that has to satisfy is basically this pattern is ordered. What I mean is if a leading entry is to the left of a leading entry in another row, then it has to be in the row above it. So that's how the ordering works. The rows are ordered by the position of the leading entry from left to right, and the rows at the top have the leading entries to the left, the rows on the bottom have the leading entries to the right. The last requirement is kind of redundant. It's almost implied by number 3, but because I think it's not explicitly stated, it has its own property, but it's not really saying much. So if a row is all 0, then it has to go on the bottom. So this is a matrix I created with some arbitrarily selected numbers, and it's in row echelon form. The leading entries are all 1s. The entries below leading entries are 0s. So you see in columns 1, 2, 4, and 5 satisfy that requirement. And all 0s, any row with all 0s is below any other row that has a leading entry. So one thing to note is that column 3 here does not have a leading entry. Same with the last column, there's no leading entry, and that's fine. There's no requirement stating that all columns have to have leading entries. And when you don't have a leading entry, there's not many requirements on that column. So you can see here that there's no leading 1 in the column 3. There is a requirement that everything here is 0 in order for the subsequent rows to have leading entries further down the line. But there's no requirement on this 8 or this 1. Reduced row echelon form is a more strict version of the row echelon form, and it's pretty much the same thing. It's almost identical. The only added requirement is that for for all entries in a column with a leading 1. Everything else is 0 except that 1. So all entries above and below a leading entry equals 0, meaning in that same column. Our first example was fairly close to reduced row echelon form. The only changes that we need to make to it to get it into reduced row echelon form is to affect these entries that exist above a leading entry of 1. So when all these turn into zeros, we've created a reduced row echelon form of the matrix. Reduced row echelon form is a more strict version of the row echelon form, but it also has a nice property that it is unique. Meaning if we start out with a matrix, no matter how I get to the reduced row echelon form, in the end it's going to look the same, no matter how I got to it. Row echelon form can differ depending on what you choose to do to the matrix. So it is not uniquely represented, but reduced row echelon is. There's only one way to express a matrix in its reduced form. So that's nice because if we both are given the same matrix, then we can agree on its reduced row echelon form. But if we were just to decide to only go to row echelon form, then we might have two different looking matrices at the end, and it might take some manipulation to compare them or see that they are the same. So now we get to the objective of what we're trying to do. Is we're trying to go through the steps of row reduction. It's also known as Gauss-Jordan elimination, and that's to get a matrix to its reduced row echelon form. So we start out with any matrix and we try to get it to satisfy these properties. That's our objective. And the way we go about it is we're allowed to use 3 types of operations called elementary row operations. What our matrix is representing, in the case of linear algebra, we can use it to represent a system of linear equations. So a matrix isn't necessarily always a system of linear equations. It's just a mathematical construct. But in linear algebra, it's useful to write a system of linear equations as a matrix. So that's the context we're talking about. And when we have this system, we can choose to express our information in different ways without changing what the system is or what the solutions are. And that's basically what we're doing with elementary row operations. I call them cosmetic changes to the equations in the system, because all the information contained in the system is preserved and the solutions are not affected. So the 3 things we can do. Number 1, we can swap the position of 2 rows. And what that basically does is just change the order we look at the equations in our system. So it doesn't change what the equations are. It just changes whether we look at this equation first or the other equation first. So the matrix itself is different. There's a distinction between having the same matrix and having the same system of equations. The matrix is apparently obviously changing because different entries have different values, but the underlying system that we're representing has not changed at all, because we're just choosing to look at information in a different order when we swap the position of two rows. And the row corresponds to a equation in our system. So the second operation that we're able to do is to multiply a row by a constant. When we do that, it's like taking an equation and multiplying both sides by some constant number. That doesn't change the equality of the statement. It's still true if we multiply both sides by the same number, but our matrix is going to look different. So that's another operation that we can do without changing our system of equations. Multiply a row by a constant number. The third thing that we can do is we can combine equations in the following way. We can just add two equations together. So if we have two equations and we add the left-hand side of both equations and we set it equal to the right-hand side of both equations, their sum, the information contained is the same. We're not changing anything in our equations, we're just putting the information together in a different way. So the three operations that we can do are called elementary row operations. They don't affect the information that is in our system, and they will make changes to our matrix, but that matrix will represent the same system. So to show the operations using an example matrix here, the first thing we can do is swap two rows. So the row in green will change positions with the row in red. The second thing that we can show is that if a row is multiplied by a constant, here we multiply this entire row by 3 and it gets replaced by the multiple of the row. And the third thing that we can do is take a row here in red. We're going to scale it by a factor. Here I've chosen to double it. And then we're going to take that amount and then add it to another row that we have in our matrix. So taking 2 times this red row and adding it to this blue row and replacing the blue row with that sum gives us this purple row here. A couple of terms that will come up when doing a row reduction, just to make things easier to state. There's a term introduced called a pivot, and that's the same thing as a leading entry, but it's specified to be a leading entry in the reduced row echelon form. So here above we had leading entries of 1s. These are known as pivots. And because this is the reduced row echelon form, these leading entries are called pivots. Otherwise, here I guess they just be called leading entries if they're not reduced row echelon matrix. So the pivot position, this can be kind of ambiguous to what they mean by position. I take it as the location, meaning row and column of a pivot. And the pivot column is the entire column that contains a leading one, contains a pivot. So for example, this the pivot columns in this matrix would be column 1, column 2, 3 does not have a pivot, so that's not a pivot column. Column 4 is a pivot column, and column 5. 6 is not. And pivot positions in this matrix would be row 1, column 1, 2, 2, 3, 4, and 4, 5. Okay, with those objectives defined and terms kind of defined, now I can move on to what I really want to do, is just to go through an example of a row reduction. And for that, I'm going to use Matlab. And I've created a script that I'm going to go through that will solve a matrix into its row reduced echelon form. So I've arbitrarily just taken some numbers and put them into a matrix. And of course I try to pick numbers that will turn out nicely, but as you can see, it's not really a simple, ideal kind of basic matrix. I try to make it more complicated, more generic, something that feels like if you can handle this, you can just handle anything. Right? It's not dumbed down to the point where you can only solve matrices of this basic type, and when you get onto a real world matrix, you're like, all right, what do I do? So it looks kind of ugly, and it's supposed to. All right, so we're going to basically go through elementary row operations to get the leading entries to be 1, to get zeros in the rest of the column containing a leading entry, and we're going to use swaps. We're going to scale rows, and we're going to mostly add multiples of one row to another row. Alright, so the first thing we can do is just pick any column that we like and scale it by a factor so that the leading term equals 1. We could always do this just by dividing out the first entry in that row. Of course, if it's a 0 that's a leading entry, well, it wouldn't be called a leading entry. If the first entry is 0, then we should look at a different row that has a non-zero first entry, because that will have to go above the row that contains a 0 as its first entry in order to satisfy the properties of reduced row echelon. So row 1 and 2 look okay to me. I'm going to do some manipulation just to make things look a little more reduced, simplified, and I'm going to divide out a factor of 2 from the first row and a factor of 5 from the second row. So in Matlab, this is the command that you can use to multiply all entries in a matrix row by a number. Well, this doesn't necessarily have to be a matrix, it's just an array which you can manipulate as if it was a matrix. So this is saying take the first row, take all entries in it, and we're gonna change them. We're gonna set them equal to 0.5, or in other words, we're gonna divide by 2. We're gonna multiply 0.5 times whatever that entry was to begin with. So we're gonna divide by 2 for the whole row. And it's nice in Matlab that we don't have to write out by hand doing these calculations, and it's presented in this nice formatted display. So the first row has been divided by 2. All right, I'm going to divide the second row by 5. So these 5s turn into 1s, and it looks a little nicer now. And we got this 1 that is a potential leading entry for the first row in our reduced row echelon form. So because there's a 1 here and it's a leading entry, I'm going to put it in the first spot on the top of my matrix. I'm going to swap the first and second rows. Matlab here is another command that will do the job. This is saying basically interchange the first and second arrays and change all the entries in that row. Alright, so number 1 row has become number 2 row, and number 2 row has become number 1 row. That's using our swap elementary row operation. Okay, so we're going to look for that pivot in the first column, and we set it up so that we already have it in the right spot. So we got our pivot, we got this row as our pivot row. And now what we need to do to this column, this first column, is to get all the entries below that leading 1 to be equal to 0. So the strategy that we can use in every situation is we multiply the first row that contains the pivot by an appropriate constant to match whatever entry happens to be below it. And then when we add the 2 rows together, they'll cancel and give us a 0. So looking at rows 1 and 2, what that means is what we do is multiply the first row, all the entries, by a constant of our choosing, and we're going to choose 2. 2 because that will make this first value into a 2, and then adding it to this row will create a leading entry of 0. So taking that first row and multiplying everything by 2 gives us this. Now we're going to use the elementary row operation where we add a multiple of one row to another. So in this case, we're going to add a multiple of the first row to the second row. Multiple of the first row is going to be added to the second row. And when we do that, that's the result. And this result we're going to replace with what we had in the second row, so that we have a 0 in that first entry spot. Alright, so this is what our matrix looks like now after doing that. We got one of these entries to be 0, and we got 2 more to go. The rest of the entries in the second row are going to change accordingly based on how we add the 2 rows together. And we're not going to really look at these values for now, but then we're going to go on the next step to manipulate this further. So for now we're just focusing on the first column and trying to get all these entries to be 0 below the first pivot. Alright, so in order to match the first row with the third row, we could scale the first row by -2 and then add them together, replacing the third row. And doing that gives us a 0 in the first entry, and these other values change accordingly. For the fourth row, we scale by a factor of -3, and adding gives us this result. So we're done with the first column. Alright, before moving on, just note that looking at the third column, it's clear to me that there's a factor of 3 that can be factored out of it. So we can scale that row using an elementary row operation. We can scale it by 1/3, or -1/3 in this case, to switch the signs. And that'll just make things look a little nicer before we do any other operations with that third row. Another thing I notice is that because this third row has a lot of leading zeros, entries with 0 to the left, I'm going to move it down a little bit because I'm guessing that in the end, when I finish my reduced echelon form, this row is likely to be on the bottom, and this row is likely to be above it since this has non-zero entries, where this row has 0 entries. So I'm going to do a row swap, clean things up a little bit before I move on. Alright, that's about as good as I'm happy with. So I'm going to move on to the second column and look for another pivot. This time the pivot's not going to be in the first row because we've already used the first row and its pivot's in the first column location. So the pivot in column 2 has to be either row 2, 3, or 4. There could be no pivot in the second column. If that's the case, then we just move on to column 3. But in this situation, it's clear that we can find a pivot because there are non-zero entries. Alright, so since row 2 is already here and has a non-zero entry in this second column, let's just try to use that one. Let's divide the second row by 7. So in Matlab, I'm using this command to change the format, and that's so the numbers will show up in a better format when I do the division. So I don't want decimals showing up in my matrix. I'm going to prefer the fraction representation. That's what this format rat does. Alright, so the second row is replaced by the second row divided by 7. So that gives us a 1 as expected, which we're going to use as our pivot. And now the second row, as expressed here, is going to be our pivot row that I'm calling, that we're going to scale by some constant factor to eliminate the non-zero entries below the leading entry in the second column. Alright, so we're going to do the same procedure we did with the first column, but now we're looking to get rid of these values, turn them into 0, by using that same procedure of multiplying a row by a constant, adding it to this row below it so that this term equals 0. In a reduced row echelon form, in addition to the entries below it having to be equal 0, the entries above that leading term also have to be equal to 0. So actually, before doing these entries down here, we're going to first have to knock out this value above our pivot. Alright, so we have to make 1 match with 1, and that doesn't take any multiplication. We can just subtract this row from that row. And that's our operation here. After doing that, we're going to replace the first row with the result of our subtraction, so that this value here is equal to 0. Okay, so the command is row 1 changes to row 1 minus this, which I'm calling the pivot row, the second pivot row. Okay, now we can move on to the row below our second pivot. And the command here, we're going to take row 3, and we're going to replace it by row 3 plus 2 times our pivot row. So the -2 cancels with the +2, and we get a 0 here. The last row is done for us, partly because we switched the ordering of the rows earlier. It's taken care of, but we don't have to do anything to this now. We can just move on. And so we had finished column 2. We're moving on to look for a pivot in column 3. So we've used the first row, the second row, we're going to ignore those. And we have to look in the third and fourth row for a pivot. Well, it looks like there's no pivot because these terms are all zeros. So there can't be any one term here. There's no non-zero terms to work with. So it's not really a problem. We just move on to the next column, and we just leave this column 3 alone. Okay, so pretending like this never happened, column 3 never happened, we skip from the second column to the fourth column. And we look in the third and fourth rows for a non-zero entry that we can turn into a pivot. So we could use this here, or we could use this here. I'm just going to use this -3, even though it doesn't look that nice. I don't want to switch the ordering of the rows. So turning this -3 into a pivot means we have to divide this entire row by -3. And we replace that row 3 with the result. And then this I'm identifying the third row, as it looks like now, as our pivot row that we're going to use to multiply by a constant and eliminate the non-zero entries in the same column containing that pivot. Same thing we've been doing this whole time. Alright, so first one, I want to take care of the first row, change that 1 into a 0 somehow. And we need to match these two numbers, match 1 with 1. Again, we don't have to do much scaling. We just subtract our pivot row from the first row. So row 1 changes to row 1 minus our pivot row here. And then it gets replaced, and this is the result. 1 turns into a 0. All these other values change accordingly. Notice that these values to the left don't change at all because of the way the ordering is set up in the reduced row echelon form. And by necessity, these terms to the left of the pivot are all 0. So that way when we add this pivot row or any multiple of the pivot row to another row, all that is affected is entries at the pivot and to the right. The entries to the left of the pivot are not changed at all, and that's very nice because it prevents us from destroying these pivots that we've already set up. So these being zeros here allows us to preserve these pivots when we add multiples of rows together. Okay, so row 1 is done because this is a 0. Now I have to change row 2 to have a 0 here. Same deal, we're going to take row 2, replace it with row 2 minus row 3. Becomes a 0 here, these values change. These values to the left stay the same. And once more with row 4 to get a 0 here, and we're going to do the same thing. Okay, so the first 4 columns have been taken care of. We only have 2 more left to go. At row 5, we're going to look for a pivot. And there's really not much choice we have left because we used up all the other rows. So the last row is going to be our pivot row. And there is a potential for a pivot because this entry here is non-zero. So like we've been doing, we divide this entire row, what little entries it has left, we're going to divide by the leading term of 5/7. And we're going to replace that row, so we get a leading 1 in the pivot column. This is our pivot row, as I call it. And then we're going to eliminate these 3 terms above the pivot, just as we've been doing. Okay, so now because there are a lot of fractions involved, when Matlab is evaluating it, it's going to have a little difficulty displaying the correct fraction in the matrix. So the term that we're getting to is 0, and it's supposed to be a 0 here, and in fact it is a 0, but because of the way fractions are dealt with, there probably is a very small number that pops out of the calculation instead of 0, just due to round off and numerical calculations of the computer. So that's why we get a star here instead of a 0. But I'll show later that these are in fact equal to 0 if it's not convincing. So what we did to get a 0 here is take the first row, subtract off the pivot row divided by 7/8. And this turns out to be a nice number, which is pleasantly surprising. Okay, we're going to repeat for row 2. Again, this is a 0, but due to display of fractions, it shows up as a star. And so we've multiplied the pivot row by 16/7 and subtracted that off of the second row, and we get a nice whole number over here. And finally, the third row, I'm going to multiply pivot row by 19 over 7, add it to the third row, get a 0 here, and a nice integer on the right. So I will show the actual number that is displayed as a star here to kind of prove that it's equal to 0. Alright, so this is the matrix that is the same as the result we've been displaying, but it's no longer in fraction form, it's in decimal form, so the zeros come out here. There's a negative 0 here, and the negative sign doesn't really mean much, it's just numerical round off. It became negative when we were subtracting stuff that's supposed to be equal. Okay, so I have to manually replace those stars with zeros, and I'm just going to display the results, correct results of our row reduction. So we can check here to see that it is in fact in reduced row echelon form by looking at the 4 properties that we need to satisfy. First property is that the first non-zero term in each row is equal to 1. The leading term, in other words, is equal to 1. For row 1, that's satisfied. Row 2, satisfied. Row 3, satisfied. Row 4, it's clear. Second requirement is that in a column with the leading entry, all other entries are 0. So that means column 1, leading entry here, everything above and below, here only below because there's nothing above, is equal to 0. Column 2, zeros above and below the leading entry, or pivot, in other words. Column 3, there is no pivot, so that requirement does not apply. Column 4, pivot here, zeros everywhere else. Column 5, pivot on here, zeros everywhere above it. And again, the last column, there is no pivot, so that requirement does not apply. So we've checked the second property is satisfied. Property 3 is the ordering property that I like to call it, and that's just saying that the pivots go from left to right, up to, top to bottom. So every pivot that is to the left of another one is in a row above it, and that's just visually verifiable by looking at the staircase pattern that goes diagonally from top left to bottom right. So we got 4 pivots out of 6 columns, and they are ordered appropriately. And the last requirement does not apply in our case because we have no rows with entirely consisting of 0. So we check that it's in reduced row echelon form, and looking back at what we started, this matrix here, you can see it looks a lot different from what we started with. It looks a lot cleaner, nicer, very easy to identify these ones, and it almost looks nothing like what we started with. But the uniqueness of the reduced row echelon form is really nice, because no matter who else I give this matrix to, and I tell them to row reduce it to reduced echelon form, anyone who does it correctly will get to the same answer as I do, if I did it correctly. So we can agree on the same system, no matter how we start out with it or how we manipulate it. And this form is very convenient to looking at the system of linear equations and finding a solution. And it's also very convenient to constructing the inverse of a matrix. Two things which I won't talk about in this video, but this is kind of the whole point, to get us there, to get us into form, know how to get the matrix to the appropriate form so that we can more easily do things like find inverses and solve systems of equations.